Okay, today we're going to look at very brief introduction into structure of metals, alloys. Why do metals conduct electricity? Why are they malleable? Why are they ductile? You can go into a lot more detail in this in courses like material science in college, but we'll just touch upon a couple things. I will say that not much of this Unit 2.4 will show up on the test, just a few questions here and there. So this is not the majority of Unit 2 for sure. So I think metals are generally solids. We have mercury, that's a liquid, but other than that, they are definitely solids. And they're not quite the same lattice structure that ionic compounds are, okay? They're gonna have something called, and let's maybe put a little highlighter here. We're gonna use something called delocalized valence electrons to talk about the internal structures of these metallic solids. So it's almost as if the electrons that are in these outer shells aren't part of individual atoms, they're just part of the entirety of the metallic solid. So I think this picture kind of gives you a pretty good indication. So the positives, you can think about that as the nuclei with the protons and neutrons. And yeah, there are internal electrons there that aren't part of the valence. And then those valence shells, the S, the P, and then with metals, also the D sometimes can be part of this. They overlap with each other, one atom to the next atom. And those electrons are able to, with metals, kind of travel throughout that entirety of that metallic solid. So some people call it like a sea of electrons. And that's going to give the ability for those electrons, because they're mobile, they can conduct electricity. And then also that sort of structure gives it a good ability to kind of have some ductile in malleability that we were just mentioning before. So here's just another picture of the same thing. We could look at this over and over again, but really it's the nuclei in the inner electrons, and then those few, sometimes a lot, other times depends on what the metal is. They're not all exactly the same. And they have the ability of those outer electrons to travel throughout the surface and conduct electricity. Lots of people consider this something called band theory, and we'll go just a very just a tiny touch upon that. Before we do that, just a little bit about alloys. So I think you may have talked about alloys a little bit last year, but alloys are a mixture. They're not a chemical composition. They're not a chemical reaction, but they are at least two metals. I guess in this case down here, carbon's not even a metal, it's a non-metal. But if you melt some zinc and you melt some copper, and you let them become liquids, you allow them to mix together, and then when they solidify, go back to a solid, they mix together those atoms and they become brass. Now, depending on the composition, how much zinc and how much copper, there's different types of brass depending on what you're trying to accomplish. But it's going to have some properties of zinc, some properties of copper, some properties that zinc or copper don't really specifically have. Like, for instance, a brass instrument, You can't really play that with zinc. You can't play a copper instrument, but you could play a brass instrument. But anyhow, if you take one atom and take it out and put another atom in approximately the same size, we're going to call that substitutional. And I have pictures of it later, so instead of me drawing it, we'll just look at the pictures. I think it might be the next slide. If you, instead of taking one atom out and adding another atom in, if you just have a smaller atom and can put it in between spaces where there are no atoms, that's called interstitial. And they're going to give those alloys different properties. So if you pack carbons in between irons, it makes it stronger. So steel is definitely a lot stronger than if you just had a chunk of iron. Substitutional is going to give you a mixture of multiple properties. Not the properties of the one metal, not just the properties of the other metal, but new properties of this alloy. So here's, I think, a pretty good picture of the two. So again, we have the substitutional. So they took, looks like, some of the coppers out and put zincs in there. Now, we do have a little problem here. This picture, it has them both pointed to the gray. That obviously can't be true. I don't know. Let's make the copper these ones. Just the fact that you're taking some of one atom out and adding another atom in, and they're about the same size. That's substitutional. And then interstitial, as you can see, the carbons are much smaller, and they can kind of fit in between where the irons are. So I'd say that probably would be maybe one multiple choice question. Okay, so going back to, I think I'd mentioned very quickly the band theory, and this is the idea about how these electrons in metallic solids are able to just freely move around and not really be, kind of quotations, owned by a particular atom. So you have, this is the outer valence band of electrons, orbital. And then you have other orbitals that are empty. Sometimes these, the next orbital that's empty is very, very far away, meaning it's not able to allow electrons to travel between these two bands. That doesn't happen. But sometimes, and I think if you remember when we were first talking about electron configurations, there's sometimes lots of energy differences between bands, we call them orbitals, and sometimes there's not very much. So a insulator, let's move that down just a little bit, and you probably know some good insulators. Heat and electricity kind of have this same idea here. So a heat insulator would be maybe a styrofoam cup. So in a styrofoam cup, those electrons that are in the valence shell aren't able to get up into the next level of electrons, and therefore they are stuck with the other atoms and they aren't free to move around. Then you might have, think of like silicone, it's a semiconductor. Maybe this valence shell band and the conduction band, another shell of electrons that empty is not that far away. And maybe occasionally you might be able to get an electron to jump up in there. If it jumps up in there, and by the way, these conduction bands, these shells, overlap with the next atom's conduction band and overlap with the next one. So if any of these electrons can get up in there, then they're free to move around. Doesn't happen that often. That's why we just call them a semiconductor. But then with metals, their outer electrons are s and p, but they also, the d orbital is actually in proximity to these two in terms of energies, and that means that the conduction band and the valence shells are very close to each other. And it's very easy, and some metals it's even easier, some metals it's a little harder. We don't use every metal to conduct electricity. If we're trying to wire a house, for example, lots of people might use copper, but I don't think a lot of people are going around in their house and wiring their house with lead for good reason, because the conduction band and valence band maybe aren't so close together. But with copper, it definitely conducts electricity very well. There's other metals that conduct electricity. I think we're not going to go around using gold, but gold is a very good conductor of electricity, and there's other ones. But the conduction band and the valence band are very close together. So there's opportunities for electrons to jump up in that conduction band, and they overlap with other atoms that are in that solid. And those electrons, once they're up in here, are free to move around. If they're free to move around, they're terrific conductors of heat and electricity. So pretty much what I just mentioned is all in that spot there. Delocalized means that they're not, quotations, owned by any particular atom, and that makes them free to move around. Okay, they don't have a Coulombic attraction to any particular atom. And we mentioned semiconductors briefly in that last 2 slides ago. And this definitely would be something for a material scientist to go into a lot more detail. This is the only detail we're going to get in our class, is that you could, if you wanted the semiconductor to conduct electricity just a little bit better, you could, we call it an impurity. Some people can even call it an alloy. You can change the conductivity properties of the material by either adding something that has more electrons, more valence electrons, or adding something that has less valence electrons. So N-type contribute electrons. So what would contribute electrons? Something that's to the right of the atom in question. So like silicon is a semiconductor. If you want silicon to conduct electricity better, or that chunk of solid, maybe take a couple silicones out and add a couple phosphorus. Why? Phosphorus has more valence electrons than silicon does. It's further to the right on the periodic table. P-type, on the other hand, maybe you want your semiconductor to conduct electricity a little bit worse. So you would take some electrons away. How would you do that? Take some of the silicones out and add something that has fewer valence electrons, like boron. Boron definitely has less valence electrons than silicon does. It's to the left of silicon on the periodic table. Here's a little picture of it. What are we using here? So we took a silicone out and added a phosphorus. The phosphorus has more valence electrons, so it's going to conduct electricity just a little bit better. Gallium is to the left of silicon. So if you substitute that one in, it's not going to conduct electricity as well. We talked about insulators. So again, if there's a big gap between the valence shell and the next, the empty shell even outside of that, then you have an insulator. If there's lots of overlap between those shells, then you're going to have something that's a very good conductor of electricity. And then of course you have a middle kind of a in between where there's a small gap there, and you might have a couple electrons get up in here, and that would be a semiconductor. And that is it.